All right, let's come to problem 8. We need to solve how many non-negative solutions do we have for this equation. All right, let's do the following. This equation can be rewritten as x squared minus x equals cosine 10 pi x. So my idea is to draw these two graphs. One graph is x squared minus x, which is parabola. The other graph is cosine 10 pi x, which is a trig function graph. And let's see how many intersections do we have, right? Let me draw the coordinate system. So this is y, this is x coordinate. Now this is a 1. This is 2. And okay, this is a 1. Because cosine function is between 1 and a minus 1. This is 0. We see that for this cosine function, cosine x has period 2 pi. Now we have cosine 10 pi x has period 1 over 5, or just 0.2, okay? That's the period, because if x changes if x changes 0.2, 10 pi x changes 2 pi, so it's 1 period. All right, let's draw this this graph or cosine 10 pi x. So I will divide this into 5 pieces. So I divide this into 5 pieces. This is 0.8, this is 0.6, this is 0.4, this is 0.2, okay? Here also I divide into 5 pieces. 1.2, 1.4, 1.6, 1.8, okay, like that. Now, for each small interval, we have 1 period of cosine. Right, let me zoom in and draw this graph. Cosine 0 is 1, so we start from here. And the cosine 10 pi x, when x equals 0.2, is also 1, so it's here. So for 1 period, it's something like this. It's very thin. Okay, I may not draw very precisely, but let me try my best. Okay, something like that. It's like this. And then again, we can repeat this pattern. Okay, let me. Okay, another period. Uh-oh. Okay. So this is another period. Okay. From 0 to 1, there will be 5 periods. Okay, let me draw this 5, and then 5/5 one. I'm trying to draw everything so you have clear intuition, but actually we don't need to draw it if you can imagine it. Of this 5 period, okay? And I like to draw some more because we need more x here. Let me draw it from 0 to 2, okay? It takes some time. Here. Okay. All right. Just one computer. Okay. All right. Now let me be slightly more careful. Just this is some point critical. Okay, basically that's enough, but let me finish by ending at 2. Okay, this is the picture of cosine 10 pi x from 0 to 2. A lot of pieces, but this is just 1, okay? This is just -1. Now, let's draw the other graph, x squared minus x. So x squared minus x. So if, because cosine is between -1 and 1, so if x squared minus x is larger than 1, there will not be any intersection. So let's try to find the points such that this equals 1. Okay, you will see that this is like x squared minus x minus 1 equal to 0. X equals, what's it, 1? Okay, we only consider positive x. We only consider positive x because we look for non-negative intersection. Plus root 5. And we see that root 5 is between 2.2 and the 2.4 because 2.2 squared is like 4.84, something like that. 2.4 squared is like 5.76. So we have something like that. And then we plug in, we see x is between, okay, this is strictly less. So that means x is between 1.6 and 1.7. That means if x is larger than 1.7, there will be no intersection because for the parabola, it's larger than 1. For the cosine function, it's always at most 1. So they cannot intersect. All right, 0.6 and 0.7 is somewhere here. So it touches 1, right? It touches 1. And now for the graph x squared minus x, this is equal to x times x minus 1, right? So we have intersection on the x-axis at 0 and at 1. And this red point. And the minimum value of x squared minus x is obtained when x equals 1/2, right? Which is -1/4. So it's about here. So if we draw this parabola, we will have the following picture. It goes to, okay, something like that. And we don't need to count the negative part. Now let's count how many intersections do we have. For each period, okay, for each period below 1.6, each period contributes 2 intersections because one go downward and upward, there will be 2 intersections. So we have totally, okay, up to 1.6, we have totally 8 periods. From 1 to 1.6, we have 8 periods. So we have 8 times 2 is 16 intersection. But after 1.6, we have 1 more intersection because for the cosine function, it goes down. For the parabola, it goes up. There will be 1 intersection. So the answer is 16 plus 1 equals 17. 17 is the solution. Okay, you can also just cross this intersection. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, and 17. Yeah. So if you can imagine this picture, actually, you don't need to draw all details, but I would like to draw it for your convenience. Okay. All right, let's come to problem 9. This is coordinate geometry problem. We have these 2 points P and Q. Well, let me draw these 2 points in the coordinate system. P is minus 1, 1. It's minus 1, 1. This is P. And the Q is 2, 2. So it's here, 1, 2. So 2 is here. And then we have this line segment from P to Q, right? P to Q. And then we'll consider the line x plus my plus m. So let me combine these two m together. So x plus m, y plus 1 equals 0, right? This is the line L. And we see that this line passing through a certain point. Zero minus 1. Okay, if y equals minus 1, x equals 0, this equals 0. So the line passing through a certain fixed point, which is 0 minus 1. So it's here. Okay. Let me call this point A. Point A. We want to show, okay, we want to see that what's the range of M such that this line intersect this PQ, the extended power from to Q, okay? Extension of the line segment PQ along the direction of Q. So we have intersection of the line with this red part, this red part. So something like that, okay, something like that. So first we know that the number M cannot be 0, okay? If M equal to 0, that means the line is just x equal to 0, no intersection. Okay, so M is not equal to 0. And then we can find the line has slope minus 1 over M. Okay, because the line can be rewritten as y equals minus 1 over M x minus 1. Okay, that's why we need to discuss that M is 0 or not 0. Okay, if it's 0, we cannot put it into denominator. So we should be very careful. So now we have the slope M equal, minus 1 over M. In order to have intersection, we should have some requirement for the slope. The slope, okay, the largest slope will be this one. It's almost touching Q, okay? Almost touching Q. So AQ has slope equals, well, the y coordinate of Q is 2, the y coordinate of A is minus 1, the x coordinate of Q is 2, the x coordinate of A is 0. So this slope is 3 over 2, okay? And then the slope cannot be larger. If it's larger, it will intersect PQ, not the extension part. All right, and we can make the slope smaller. And the limit will be, okay, we can make it smaller. I will still have intersection, but there's a limit. The limit will be that this is parallel to PQ. This is parallel to PQ, then we don't have any intersection. So the limit will be, let me do this way, the slope of PQ, that's equal to 2 minus 1, 2 minus negative 1, which is 1 over 3, 1 over 3. So the slope must be between 1 over 3 and 3 over 2. So minus 1 over M is between 1 over 3, strictly between, okay, and 3 over 2. From here, we can solve the range of M. Will be minus 3 less than M, less than minus 2 over 3. And then we know what is A. A is minus 3, B is minus 2 over 3. A plus B is minus 3 minus 2 over 3. which is minus 11/3. The solution is B. All right, let's come to problem 10. This is a solid geometry problem. We have a rectangle ABCD. Such that AB is √2 and BC is 1. So now we rotate this rectangle along its diagonal AC. We rotate this along its diagonal AC. So we get some 3D object, 3D solid. We want to calculate this solid's fallen, okay? All right, let me first try to draw this picture, and you have some intuition, okay? So let me do this. Let me rotate a little bit. And let me try to draw this, okay? And then we rotate, right? So this is A, B, C, D. So we rotate, you will get something like this. Let me use red color. You will have something like that, right? For the upper part. And then you rotate here, you get another part, something like this. Okay, and the lower part will be symmetric. And this part is also like that. We have some solid like this. I hope you can imagine this figure. Now we see that this is symmetric. This is symmetric. So we will do the following. We like to, okay, the middle part, this middle line is like the middle point. The upper part and lower part will have the same volume, okay? In order to calculate the whole volume, we only need to calculate the half volume and then multiply by 2. So the half volume, what is half volume? Equals the solid. Okay, let me put some notation to okay. Do you know this? Suppose I draw this DM perpendicular to AC, and this middle point, I draw the middle point of AC is N, and the EN is perpendicular to AC, okay? So basically this is like the point E. This is the M. This is N, okay, this is N, right? So half volume corresponds to this solid, the volume of this solid. Right? AD, this is E. This is like a half volume. And this half volume equals the following. This is like, okay. Let me connect this. This is a big solid minus a small cone. Do this. Okay, this is A and D. Here it will have C. This whole. This is like a two cones, the union of two cones, minus this small cone. Here is E, okay, E. Minus this small cone. Okay. Now let's calculate these two pieces. For this big one, it's basically the sum of two cones. The formula for the volume of the cone is 1/3 pi times the radius. Okay, here the radius is dm. okay, dm. Let me call this radius r. And en is small radius, so let's call little r. So this is r squared times the height, am, okay, am. That's like the upper cone. And also we have the lower cone. So this MC. Okay. So we have this M here, this upper cone and this lower cone. So this is the volume of the big solid. And then minus the volume of the small cone. We still have formula 1 over 3 pi times En squared. En is little r. N is here, right? This N here, little r. Little r squared times the height. The height is Cn, okay? Which is just 1/2 of AC. So we can calculate all these numbers. 1 over 3 pi. So now what is capital R? We can calculate R by using the triangle ADC. AD times DC equals AC times DM. DM is the R times R. So R is AD times DC divided by AC. AD is 1, DC is √2, and AC by Pythagorean theorem, we know it is √3. So R is √2 over √3. And the AM plus MC is the diagonal, which is √3. Okay. And then times 1 over 3 pi times little r. Now let's see what is little r. Little r, we know Cn or NC. Cn is 1/2 of AC, which is √3 over 2. And we know triangle CNE is similar to triangle CDA. So the ratio between Cn and the En is √2. So that means En, which is just little r, equals Cn divided by √2. So this is √3 over twice √2. So that's little r. Okay, now Cn, we already know Cn is 1/2 of the diagonal, √3 over 2. And then we calculate this, or we see this equal to 23 √3 over 72 pi. So that's the volume for okay, sorry, this should be 144. 144, okay? And then the answer is, this is just half volume, okay? This is just half volume. Okay? And the answer is twice of this half volume, twice of this, which is 23 √3 over 72 pi. Okay, that's the answer. Okay, let's do problem 11. So we have a triangle. It's a right triangle with side lengths 3, 4, 5. So we want to use a square to contain this triangle. What's the minimum side length of this square? All right, let's try to see what's the relative position between this triangle and the square. So first we know that this triangle 3, 4, 5 can be contained in a square like this with side length 4, okay, with side length 4. So 4 works, but maybe 4 is not the minimum side length. So let's try to minimize this side length. So what we can do is to tilt this triangle. Maybe something like that. And then we draw this square. Maybe like that. So maybe we should tilt it more. maybe we should tilt it like this. So this point touches the vertex of the square. Okay, I think the third one is the right picture when the side length is minimized. All right, now let's try to solve this side length. Suppose the side length is A. How do we solve this side length A? So there are typically two ways to solve it. Let me first present the method one by geometric approach. Okay, so let me draw it here. So I will mark A, B, C, D, and this triangle is three, four, maybe 5 here. Okay. Right. Okay. Geometric method is as follows. I'd like to rotate this triangle. Okay. I should mark 2 more points. This is P, Q. Okay. I will rotate the triangle BCQ. So triangle BCQ. I rotate this by 90 degrees clockwise. So I will get triangle here. Okay. So here, let me call this point R. So that means we have angle QCB equals angle RCD. So that means we have angle QCR equals angle BCD, which is 90 degrees. So that means angle QCP plus angle PCR is 90 degrees. And we also know that angle QCP plus angle QPC is 90 degrees. So we have angle QPC equals angle PCR. Okay, these two angles are equal. Right, now I can basically draw this altitude from R to PC. So this will be 90 degrees. So that means we have the similar triangles. Triangle Q, triangle PQC, right triangle PQC is similar to right triangle C, okay, let me call this H, CHR. Okay, these two triangles are similar. Maybe let me probably show you this triangle and this triangle. They are similar. They are similar. And now we can calculate the length of CH because RC is QC. So this is also 4. Okay, and for PC is 5. So we can calculate CH is 3/5 times hypotenuse 4, which is 12/5. And RH is 4/5 times 4, which is 16/5. Okay, and we know CP equals 5. So we get that PH equals 5 minus CH. So 5 minus CH becomes 13/5. That's pH. All right, we have both pH and HR, so we can solve PR. PR is pH squared plus RH squared, and then we take square root by our Pythagorean theorem. So this becomes 17 square root. All right, Now, our goal is to solve the side length CD. We know that based on the formula of the triangle's area, we know that PC times RH equals PR times CD. So CD is PC times RH divided by PR. And we already have all this lengths. PC is 5, and RH is 16 over 5, and the PR is 17. Okay, square root 17. So this is 16 over root 17, which is 16 over 17 times root 17. Okay, this is basically by a geometric approach. Now let me give you another approach. Maybe it's faster. It is by solving equations. That's the 2. Okay, we still use this same picture, but this time we don't rotate. Let's say A, B, C, D. Three, 4, 5. Okay, this is not a good picture. Let me redo it. Maybe somewhere here. Okay, somewhere here. Okay, so A, B, C, D, P, Q. So I will do the following. I will set AQ to be X. Okay, so AQ to be X. AQ is X, and then we see that AP, by Pythagorean theorem, AP is PQ squared minus X squared, and then we take square root. So it's 9 minus X squared with square root. All right, we know that triangle QAP is similar to triangle CBQ. Let me mark here. 9 minus X squared. So we can use this, the ratio between the side lines is 3 to 4, because the hypotenuse is 3 and 4. So that means we can find the side lines, okay, QB. QB is 4 over 3 times AP, which is 4 over 3 root 9 minus X squared. Okay. And then we have BC. BC is 4 over 3 times AQ, which is 4 over 3x, right? And then we set our equation by knowing that AB equals BC. This implies X plus QB, okay, equals BC. So BC is 4 over 3x. And then we can combine these two x, and we get that 4 over 3, 9 minus x squared equals 1/3 x. And this is basically 4, 9 minus x squared equals x. And then we square both sides. So 16 times 9 minus x squared equals x squared. And that means we have 144 equals 17 x squared. So x equals 144 divided by 17. We take square root. That's 12 over root 17. And then we want to find the side length. So BC is the side length, which is 4 over 3x. So it's just 4 over 3 times 12 over root 17, which is 16 over root 17. So we'll get the same solution, 16 over 17 times root 17. Right, we get the same answer, 16 over 17 times root 17. That's the solution. Okay, let's do problem 12. So we have this triangle and it divided into two parts. Each sub-triangle have a in circle, okay? We would like to calculate the ratio of these two radii, right? And then let's first record the formula to calculate this radius for a given triangle. So, okay, let me draw a triangle. Suppose we draw this in circle. Okay, we draw this in circle, and we know the radius. Let me denote the radius by r, and say we have this. Suppose we have the side lengths of the triangle to be ABC, A, B, C. All right, we know that we can divide the triangle into 3 pieces. So, okay, maybe let me still denote by A, B, C. So the area of a triangle, so this notation means the area of triangle ABC. This equals the area of 3 triangles, OAB, plus the area of triangle OBC, plus the area of triangle OCA. Okay. And then we know that this radius start from center is perpendicular to this side, right? To this side. So this corresponds to the height for these sub-triangles. Now we can use this to express the areas. So 1/2 OAB. So the base is AB, the height is the radius R. So this is 1/2 C times R. OBC. BC is the base and the radius is the height. So that's 1/2 A times R. OCA is the base is AC, which is B, and the height is R. So we have this formula, 1/2 of A plus B plus C times R. So the radius of the incircle is twice the area of triangle ABC divided by the parameter A plus B plus C. Okay, so let's record this formula. And then we apply this to our problem here. Okay, so in our problem, we have this big circle. Okay, let me redraw the picture. Okay, let me just mark in our picture. So we have AB equals 12 and AC equals 8. And we just know BD equals twice AD and equals twice CD. And we don't know the exact length, so we can just set it by numbers. Say, suppose AD is X. And DC equals AD, so it's also X. But BD is twice X. Okay, so this is X, this is X, and this becomes twice X. And in this way, we can express the parameter. All right. The big radius is R, capital R. The small radius is little r. Okay. So we know capital R is twice the area of triangle ABD divided by the parameter of triangle ABD. The parameter of triangle ABD is 12 plus X plus 2X, which is 12 plus 3X. Okay, and for the little r, this is twice triangle ADC. Okay, divided by the parameter 8 plus X plus X, so which is 8 plus 2X. All right, And we also know the relation between these two areas because triangle ABD has base BD is the twice of the base DC for triangle ADC. And they will have the same height, okay, because they share the common vertex A. So we have that area of triangle ABD is twice the area of triangle ADC. Okay? And then we can divide it, right? So R divided by capital R is twice ADC, 8 plus 2x, divide capital R, that's multiplication by 12 plus 3x, divided by twice triangle ABD. Okay. So we know that ADC is twice ABD. So we can cancel this and replace by 2. And the other part is exactly 3/2. Okay, so 12 plus 3x divided by 8 plus 2x. This is exactly 3/2. Okay, I made a mistake here. I should put 2 here, okay, because ABD is twice of ADC, so 2 should be here. Right, so basically 2 cancels 2. Okay, so this is 3/2 times 1/2. Okay, 3/2 times 1/2, which is 3/4. So the answer is 3/4. Okay, all right, let's come to problem 13. It's a probability problem. So we have a line segment of length 1. So let me draw a line segment, length 1. And okay, 0, 1 here. We choose 2 points randomly, right? And okay, this line is divided into 3 regions, A, B, C. Let me first mark these regions. First region A, the second region B, third region C. And then I want to denote the length of this segment by notation. So suppose the length of the region A is, let's say it's A, little a, okay? And the length of B is little b. And of course, the length of C is 1 minus A minus B, okay? So here we just assume that these regions A, B, C are just three line segments. But the problem didn't say there are 3 line segments, maybe they're just 3 regions. But, so in general, maybe it's more complicated, but it doesn't change. We can just assume there are 3 line segments. So suppose A has 2 parts. So A1, maybe here A2, maybe this is B, maybe this is C. So we can always simplify the general case into the simplified case because we can just combine A1, A2, put together and into a single line segment. Okay, so let's just assume A, B, C are just 3 line segments. All right, now we choose 2 points from these regions. The probability that they are in different region is 35/72. The probability that one in A, the other in B is 1/9. So choose 2 points randomly. That's equivalent to choose a point in this 1 by 1 square. So we can draw this coordinate system. X, Y. Okay, this is a 1 by 1 square. So we choose X and Y. From this line segment, let's just choose a point in this square, okay? So I will divide this square into several regions according to this line segment ABC. So A is here, B is here, maybe A here, maybe B here, okay? Accordingly, right? So this lines divide the region into 9 regions. Okay. Now let's find the expression of these probabilities. First, the probability that they are in different regions is 35/72. So I like to calculate the probability that they are in the same region and then subtract this from 1. It's 1 minus, okay, if these 2 points are in A, that means this is A squared. If these 2 points are both in B, that's little b squared. If these 2 points are both in C, that's just 1 minus A minus B squared. Then I subtract this number from 1. That's probability that these 2 points are in different regions, which is 35/72. Okay. B is A region. All right, and we have the second probability. If one point is in A, the other point is in B, that's 1/9. So there are 2 regions. One is here, the other is here. And the area is just XY. So we have twice, okay, sorry, A times B. We have twice AB equals 1/9. This is what we know. So our goal is to solve the length of C. The question is, what's the length of C? Okay. So we transfer the probability into this algebra problem. All right, from the first equation, we know that we have A squared plus B squared plus 1 minus A minus B squared equals 1 minus 35/72. So this is 37/72. And I'd like to add twice AB. So I want to complete the square for AB. So let me do add 2AB here. So I will have the following: A squared plus 2AB plus B squared plus 1 minus A minus B squared is 37/72 plus 1/9, okay? Because 2AB is 1/9. And then the first 3 terms is basically A plus B squared. So totally we can do the following. We have A plus B squared plus 1 minus A minus B squared. This equals, this equals 5/8. Okay, 5/8. Now, okay, remember our goal is to solve 1 minus A minus B. Okay, so let me do this. Let me set 1 minus A minus B be T, okay? And accordingly, A plus B becomes 1 minus T. Okay, let's try to solve T. So this is 1 minus T squared plus T squared equals 5/8. And then we can expand this square. Finally, we have twice T squared minus twice T plus 3/8. Okay, 3/8. Let me see. Yeah, let me expand to avoid mistake. 1 minus 2T plus T squared plus T squared is 5/8, right? And then we have this quadratic equation. I mean, (3/8) equals 0. Okay. All right. Of course, we can divide this by 2. T squared minus T plus 3/16 equals 0, and we can vector this quadratic equation. This is T minus you see 3/4. T minus 1/4 equals 0. So it's very clear we have 2 roots, 1/4 or 3/4. but only one number is the correct answer. So let me explain why. I will claim that the 3 over 4 is not the right answer. If, okay, t equals 3 over 4. Remember, t is 1 minus a minus b. So we have a plus b equals 1 minus t, which is 1 over 4, right? So we have the following. We know that 2ab equals 1 over 9, but 2ab is less equal to a squared plus 2ab plus b squared, which is a plus b squared, which is 1 over 16, right? 1 over 16. But on the other hand, we know that 2ab is 1 over 9. This is a contradiction. 1 over 9 cannot be less equal to 1 over 16. So we must have t equals 1 over 4. So 1 over 4 is the answer. All right, let's do problem 14. So what's the largest possible positive integer n such that the sum of these two powers is an integer? All right, let's do this first. So 37.5 is equal to 75 over 2. And 26.5 is 53 over 2. So the problem is equivalent to 75n over twice n over 2 to n plus 53n over 2 to n, which is 75n plus 53n over 2n. So it's equivalent to discuss what kind of n make this quotient an integer. Okay, so this is an integer. Implies that 2 to n divides this sum. Okay, that's the equivalent statement, right? What's the largest possible n this holds? Okay, I would claim the following. Okay, we can discuss the evenness of oddness of n. So if n is even, case 1, if n is even, we know both 75 and 53 are odd numbers. If n is even, we have 75 n is 74 plus 1 to even's power. So n may be equal to 2k, for example, n equals to 2k. So we know that for odd number with even power, this number, when it's divided by 4, the remainder is always 1. So we have remainder 1 when this is divided by 4. Okay. And similarly, we have 53 to the nth power is 52 plus 1 to 2k. So it's again odd number with even power. So the remainder is 1 when it's divided by 4. Okay. So we see that 75 nth power plus 53 nth power. The remainder is 2 when it's divided by 4. But on the other hand, if n is an even number, we have that 2 to the n is 2 to 2k, which is 4 to the k's power. The remainder is always 0 when it's divided by 4. Okay, that means in this case, we don't have this divisibility. 2 to n does not divide 75n, 53n. Okay, so this, in other words, the original quotient cannot be an integer. Now let's discuss the case that n is an odd number. Okay, and here if if n is odd, okay, if n is odd, now let's consider this sum. We know for n for power to be odd number, this sum could be factored as follows. 75 plus 53, 75 n minus 1 plus 75 n minus 2, 53, dot dot dot, 75 times 53 n minus 2, the last term is 53 n minus 1. Okay, this sum can be factored. And we know that this equals, the first parenthesis equals 128, which is 2 to the 7th power. And for a later part, each term is a odd number because they are all odd number. So let's count how many terms here. So we have totally n terms. Odd number terms of odd numbers. In other words, the later parenthesis must be odd number. So in order to have 2 to the n divide 75n plus 53n, this is equivalent to 2 to n divides 128. But 128 is 2 to 7. So the largest possible n is just 7. Okay, that's the solution, 7.